visible, right? And I'm audible, right?
Yes, yes, yes.
Yeah, yeah. So is today's agenda clear?
Um, yes, now the screen is we can see the screen
Yeah.
very clear now.
Okay. Yeah. So in previous session we have seen the FPGA inside view, like what are inside the FPGAs, like LUT, CLB. What is a CLB? And we have discussed what is this FPGA logic block, and we have seen lookup tables. What is meant by lookup table? How it is performing the operations, and we have seen the internal architecture, right? So we will come directly to the block diagram of our modern FPGA actually. So nowadays in modern FPGAs, what are all the facilities we are having in this FPGAs? We have DSP slice in the FPGA itself, so it is embedded in the FPGA, and we have RAM also, which is embedded inside our FPGA. So this is all the fabric. This is the FPGA fabric. Inside this only DSP slice is also available, RAM is also available, and we have also CPUs. That is, it is a processor is also available in our FPGA only. So for example, Zinc processor. Uh, this is an example where we have uh, processor as well as processor is embedded into the FPGA. Okay, so instead of connecting our FPGA to an external processor, like this, we have the designs. The Zinc is made such that the processor is embedded into this FPGA only. Okay, now, so in this modern FPGAs, we have DRAM controllers, USB controllers, Ethernet controllers. We have, so if you want to if you want anything to happen, like uh, let's say for example, do you have any idea about SoC, system on chip? Any idea about SoCs, system on chip?
Just basic ideas.
Yeah. So for example, if we have a chip like this, system on chip, and in this chip we have FPGA like this, and if this FPGA wants to communicate with the external memory, and this chip is having some IO interface, input output interface like this, like USB interface or some UART interface like this. And if the chip wants to communicate with the external world, like USB, through USB or UART, so to control this IO, we need a processor or a controller. Okay, we need a microprocessor or a controller, right? So this will basically what happens. This will take the data from the outside world, and it will process the data, and it will pass it to the FPGA. So the FPGA will perform all the logical operations to the data. Required operations are done, and the results are given back if needed. Okay. Is the need of the processor clear?
Yes, yes, very clear.
Yeah. Yeah.
What about the RAM? Why there is a RAM inside the FPGA?
RAM is basically a storage device, right? So if you want to store anything in anything, so instead of connecting an external memory, you can store it in the FPGA only. Okay. Is it clear?
Yes, yes, yes.
And the DSP slice also. So instead of connecting any other DSP for any other performing DSP operations, you can have you are having DSP slices inside the FPGA only. So you can perform any DSP operations using the FPGAs. Okay, that all we will see in upcoming sessions. So these are all the internal components of an FPGA. Okay. Now, so coming to the uh, Bitstream. Wait a minute. So say suppose if you want to implement a logic, so if there are any two inputs, say A and B, and this is our design, and this is my output. So my output is equal to A XOR B. So this I want to implement using an FPGA. So how can I implement this operation? What I'm doing XOR between the two inputs, that is A XOR B. So this operation I want to implement using an FPGA. So how can I implement this operation using the FPGA? So first what you will do is you will write the Verilog code or VHDL code. Okay, so there are two languages. One is VHDL, one is VHDL. Okay, very high speed description language, and Verilog. Okay, so these are the two languages available through which you can write the code, through which you can write this logic A XOR B. Okay, so using that you can write the logic, and after writing that logic what you can do is you can synthesize the design. I will show how you will synthesize the logic which you have written. So synthesis is nothing but converting the HDL code into a gate level netlist. Okay, so synthesis is nothing but converting the code which you have written into a gate level netlist is called the process of synthesis. Okay. So this process actually translates the high level design into a lower level representation that is easier for the FPGA to implement. Okay. So the code which you have written will be in a high level language. So that will be converted into a low level netlist. Now, after synthesis, what happens is you will go to implementation, this one. Okay, so using the implementation you will basically translate the netlist into a format suitable for FPGA, and you will be doing mapping. Okay, so this all steps are performed by the tool itself. I will show how the tool will be performing all the steps. So all the steps will be performed by the tool itself, and after mapping, place and route operation will be happening. So basically what is this place and route means, physically placing the logic cells onto the FPGA and do the interconnections between them. We have seen in our previous session, right? So the interconnect, wait a minute, I will show you. Yeah, so this is the connection of all the logic cells is called placing and routing, and placing of all these cells is called placing and routing. This we have seen in our previous session, right? So this placing and routing will be done by our tool only. So this step, that is placing and routing, will also be done by our um, EDA tool, and after this implementation the bitstream will be generated. So basically, a bitstream is nothing but a configuration file which tells the FPGA that how many slices should be active and what are all the slices should be active. So that bitstream or configuration file will be telling our FPGA like how many cells should be connected, how many cells should be connected to each other, or what is the route between the cells. That all will be stored in a bit file. So that bit file we are going to generate using the tool. So what is happening? The Verilog code or the VHDL code you have written will be converted to a bit file. Okay, so the extension for that file is bit file dot bit. Okay, so that file you will be dumping into the FPGA. That process we will see later. So for today's session we will be stick on to how to generate this bit file. So basically the code which you have written will be converted into a bit file and it will be loaded into the FPGA. It will be loaded into the FPGA. Okay, so where it will be stored into the FPGA, that is all secondary. We will discuss about that. So in this session we'll see how to generate this bit file. So is this clear why we are generating this bit file and how we are creating? Is it clear? So this is a definition for bit file. So bitstream. Okay, so a bitstream file that can be loaded onto the FPGA. So this file contains all the configuration information needed for the FPGA to implement the design. So this is the bitstream file. Okay, is it clear what is this bitstream file and why we are creating it and what are the steps? Is it clear? Is it clear? Right? Can we move on?
Yes, yes, clear.
Yeah. Now, so this is the interface of Vivado. It is 2023 version, and so when you open this Vivado, you will see this type of interfaces where you can see the recent projects on the right hand side, and on the left hand side you can see three options. One is quick start, and another is task, and the third one is learning center. So you can find documentations and tutorials, and you can refer quick take videos like that. And in the task, you can manage IPs. IPs are nothing but intellectual properties. So there are many IPs in the Vivado that also we will see. And you can also connect to your FPGA via the USB cable to your system, and you can open this hardware manager like this. And in the first section, you can see in the quick start there are three options: create project, open project, and open example project. Now we are going to create a project. So after clicking it, click the next, and you can give the project name, and you can specify the project location. Next, and here you can mention the what type of project you are going to do. So there are basically one, two, three, four, five sections. So first section is RTL project, and second section will be post synthesis project. So you will be able to add sources, view device sources, run design, analysis, planning, and implementation. This we will see in the upcoming sessions. For now, we are going to create a RTL project. RTL is nothing but register transfer level project, and we will click on do not specify sources at this time. Now, next. So yeah, here you can select
What option? Sorry for interrupting. What is this option? Do not
which one. Do not
do
specify
not
the sources at this
specify.
time. Okay.
What is this option?
Yeah, I will show it. So yeah, I will show it in the. I will show it later. Okay. Yeah. Next.
Okay.
Next, you can select the type of the board. Okay. So the part number is here. So for every FPGA, you will be having specific part number. Okay. So that part number, according to that part number, you can select. So for searching for like adding filters, you can select the category and family. Like there will be Artix A7, Kintex, Spartan, Vitex. Like this, there will be different families of FPGA. So if you are using a Zinc FPGA, then you will press Zinc. So all the Zinc family FPGAs will be displayed. So according to the part number you are using, so according to the FPGA part number you are using, you can select that particular FPGA. And package also you can select it, and speed, temperature, static power, like that you can select it. And so just selecting randomly. So I'm selecting this Zinc, and I'm selecting this part number. Next. So this is a project summary. So a new project named project underscore one will be created, default part and product. Next, finish. So it will create the project for me.
This kind of software can be used only with Xilinx FPGAs, right?
Yes. So Vivado is being supported for only Xilinx. Okay. So if you are using
Yes.
Intel based FPGAs, then you should use Quartus Prime.
Quartz.
Yeah.
Okay.
Now, so we have selected do not specify sources at this time, right? So let me create one more new project. So I'll press next and next. So I'm disabling this option. So here, when we disable that option, one more window will open for us if we press next. So here it will add whether you want to add the file, that is an existing file, or you want to add a directory, or you want to create a new file. Like this it will ask. So if we press like that, So if we disable the do not specify sources at this time, so a new window will open like this. Okay, is your doubt clear?
Yeah, yeah, yeah.
Yeah.
So add it to a reference sources. It will make us have all the FPGA series and families, and we select the one that we are using.
Yes.
Right? Am I right?
Yes.
Yes,
Yes.
yes.
Okay. Now,
Yes, got it.
yeah. Now we have selected initially do not specify sources at this time. So this is the interface we have we are getting after everything. So if we want to add some sources like Verilog file or VHDL file, then you can simply what you can do is you can press on the design sources and right click on it, and here at the end you can see add sources. So here you can sources will be of three types. One is create constraints. We will discuss what is constraints also, and design source and simulation source. So now I want to create a design source. So I will press on it and click next. Now again this window will open. So you can press on create file. Okay. So you can give some name, example, file name is example, and file type is Verilog. You can keep Verilog header, system Verilog, VHDL, or memory file. For now, I'm using Verilog, and file location is local to the project, and press OK. Finish. So it will create the source, and here you can specify the module name, port name, all that, but I will keep as it is. Yes. So everyone is getting that. Is it clear for everyone?
Yes. The module name here is example, right?
Yes, it is automatically given the model name as example.
Ah, okay. The question here is, when I start writing the Verilog code,
Yeah.
is it must to write the name of the module in the Verilog to be example as well, right?
No, no. You can change the model name if you want, like this. For
Because
example.
in Quartus it do error
Yeah, yeah. In
if the
quarters,
module name.
yeah, in quarters it will throw an error because if you have created a project name which is different from the name which you have written as model in the file, it will throw an error. Yeah.
Yes, yes.
But here there is no problem. You can take different names. Okay.
Mm-hmm, mm-hmm.
Yeah. Now
Got it.
here you I've created a model test, and for this input is a b, and output is my v, sorry, y. Assign y is equal to ax or with, and I'm saving this file. Okay. Now, so if you want the layout to be reset, then you can go to the option layout and press on reset layout. So the layout will be reset. Okay. Now, so you have written your design source, and if you want to simulate your source, you can uh, go to the simulation sources. So in that simulation sources, you can again right click on it, and you can press add sources, and here you can press the third option, add or create simulation sources, and press next. And here you can create a file, and you can give any name, test underscore tv. Okay. And press finish. Now press OK again. Yes. So your simulation file will be created. So you can write the test bench and you can simulate it using the simulation window. I will show you.
Can I ask a quick question?
Yeah, yeah.
What is the layout? You have hover over layout, and
Layout.
then you choose reset layout. What is this option?
Yeah, I will show. So after pressing this test underscore tb, my file will be open, right? So if I maximize this file like this, float and maximize. So if I want to reset my layout, then what can I do is I can go to my layout and reset layout. Okay. So when I open the project or when I have created the project, what layout I was having, it will come to that same layout. Okay.
Mm. I didn't got this point. What
So
has happened?
okay, okay. Wait a minute. So basically, it's an optional. You can use or not use, no problem. Anyways, I will show it. So like this, I have changed the layout, and if I want to reset the layout, then I can go and reset layout. So my layout will be into my initial position like this. Now is it clear?
Mm.
So,
Yes, yes.
sir, why do we use the layouts?
Layout is nothing but the screen you are seeing. So for example, if you want to reset the layout to initial, like when you have created your project, what layout you're having, so to that, so now I've changed this layout like this. So these are three windows, right? So if I go to layout and press reset layout, I will come to my initial layout like this. Okay, that's it. It's a simple.
Yes, yes, yes. I thought you are doing something in the very low code. That's why I have asked you again.
Yeah, yeah. I've
But it
written.
is only changing the view of the Vivado tool.
Pardon? Can you repeat it again?
Yeah, yes, yes. What this layout is doing actually, it is only returning everything in the Vivado view
Yes,
and the
yes,
Vivado graphical user interface to its
yes,
place
yes,
again,
yes, yes.
to
That's it.
its original place, right?
That's it.
Yeah. Yeah.
That's it. Yeah. Okay. Now, so you have created a test bench file. So if you want to maximize it, you can press this, or you can press the float button. So it will float, and you can maximize it. And you can write the test bench for your design. And so if you want to test your simulate your design, so in the left side in the project manager section, you can see in the simulation section, here you can press run simulation and press run behavioral simulation. So the simulation will start running. I haven't written any test bench, so I will not get any exact particular outputs. So it will take some couple of minutes or seconds, depending upon what type of processor you are using in your system requirements. The speed depends. Yeah. So like this, three windows will be having similar to model sim. I hope you have used model sim, right?
Mm-hmm. Mm-hmm.
Yeah. So like this, you will be having the window to check the outputs, and you can test the outputs whether you are getting it or not, and you can close the
Yes,
simulation.
can you show us? Can you show us, please?
Like I haven't written
I want
any.
to assign values
I haven't written
for the
any
input.
test bench, right? So I cannot see anything. I haven't written any test bench.
But in Quartus, I think the behavioral simulation or function simulation in Quartus, you can assign certain values for these inputs without
Yes,
writing a
yes,
test
yes.
bench.
Here also we can
Is it
assign.
possible here?
Yes, we can also do force constant. Okay, so we can do that, but that is not the agenda for this session, so I'm skipping that part.
Mhm,
Okay,
mhm, mhm,
we will discuss that in future. Okay, yeah.
mhm.
So like this, we can.
But I didn't understand. Sorry.
Yeah,
I
yeah.
didn't understand what is the role of the simulation file that you have created. What did this simulation file do?
This test bench file. So
Ah,
you
yes.
can attend my actually Verilog sessions. Okay, so there I have explained. So I will share the link. Okay.
Mm-hmm,
So
mm-hmm.
if I started, then
Yes.
it will take more time. Okay.
Mm-hmm, mm-hmm. Okay.
Yeah. Next. So after simulation, you have satisfied with your simulation, then you can go to synthesis. You can press run synthesis. So your design will start synthesizing, and after synthesizing, your netlist will be generated. So in that netlist, you can actually, after synthesizing, getting synthesized, you can, this option will be enabled. Now it's disabled because you have not started synthesis, and after completing synthesis, this will enable, and after this you can press run implementation. Okay, so the netlist file will be routed, placing and routing will happen, and after that, finally you can click on generate bitstream. Okay, so the bitstream file will be generated, and it will be stored in the directory which you have created. For example, here it is the project directory is d gaurav ambar protocols project 1. So in this local to this directory bitstream file will be stored. So that bitstream file, you are going to load it into your FPGA. So that how we are going to load it into our FPGA. Wait a minute. Yeah. So the generated bitstream file using the Vivado, that how we are going to export it into our FPGA, that we will discuss in next session. Okay. So is it clear?